You can ensure. What? Oh. This helps us out. This is hard. This is complicated. I'm thinking about backtracking, but we'd have to backtrack and then sort every time, which isn't efficient. Oh, wait. We don't even need to sort. No way. That's crazy. I didn't even know that was going to work. I was thinking about it. And I was like, wait. This definitely helps us. That's crazy. I can't believe I got it. I was actually very surprised that I got it. Let's see. Bruh. This is too much, bro. This is too much. There we go. This is too much. Solution 2 is pretty neat. Did I do solution 2? Yeah, that's what I did. Wow. Is that really the constraint? Is constraint 1 to 10? Oh my gosh. That's crazy. I didn't think that was going to work. I thought there was going to be some sort of edge case. Oh my gosh. I surprised myself there. Pretty sure this is it. That's crazy. I was about to look at the answer. See, this hint would have... Oh, you can't see the hint. This is the hint. That hint would not have helped me. Wow, that's a fluke if I've seen one. I don't know if I was given a problem like that again. I don't know if I'd be able to get it. I really don't know. I really don't know. Okay, nice. Okay, so container with the most water. To solve this, use a two-pointer method, and we'll take this array. We'll have a left pointer and a right pointer, and we'll calculate the amount of water we can store between these 2 points by taking the minimum and multiplying it by the distance between these two. And then we'll store a max variable. And then we decide which pointer to iterate based on which one is smaller. And we slowly start closing in the window. So it'll be like this. It'll be 1, 7, 8, 7, 8, 3, 8, 8. And depending on how I set it up, we can go 6 or 4. So let's just go 6, 8, 2, 8, 5, 8, 4, 8, and it'll calculate all the areas there, and we'll store a max. We'll store a max for all those iterations, and we'll be good. So we make some max variable here. We make a left pointer and a right pointer. Oh, right, length -1. And then while left is less than right, we are going to calculate the current area. So we take the minimum between height left and height right, and we multiply it by right minus left. And then max will equal mat.max between itself and the current area. And then if the height of the left is less than the height of the right pointer, we're going to increment the left. Otherwise, we're going to decrement the right. And then we'll return max. There we go. So this is going to be O of n time complexity, O of 1 space complexity. Okay, so this is a very similar problem. Basically, we're going to have a left pointer and a right pointer, and we are going to store a max variable with all the water, or sorry, not a max variable, but a total water variable. And we're going to look at each of the pointers and say which one is smaller. We know that this is smaller, and because we're for certain that this left pointer is smaller than this right pointer, we know that the difference between these two is the difference between the two is the potential amount of water that we can add. So 1 here, because 1 minus 0 is 1, right? So we know we can add at least 1 here. And then we will increment that. Here it's even, so we know nothing happens. And then we increment one of them. So let's decide to increment here. Here again is 1, right? Here is 1. And then here is nothing. And then here is 1. Here is 2. So you can see it's 1. Actually, how are we handling this? Maybe I don't know how to explain this. We also have to keep a rolling max. Okay, wait, I'm gonna give me a second, let me check something. Okay. So let's see. Oh. Oh, that's why. There we go. Alright, I need to walk through this code to understand it. Because I know the code, but I can't explain it, so. Max left is going to be 0. 0 minus 0. Whatever. Uh-oh. 1, 1. We're going to go on the right side this time. Water's still 0. Alright, 2, 1. We're going to go here this time. So we had 1. Max left is still 1. So this does nothing. Then we go here, max left is still 1. So this is now 1. Then we go here, max right is 2. We don't do anything. Max right is 2, so we add 1 here. Max right is 2, we add nothing. Max right is now 3. Max right is 3, so we add 2. Wait. Oh, this is tricky. Oh, wait, that's why we don't go here. So max left is still 2. We don't do anything. Max left is 2. We add 1. So it's 3 now. Max left is 2, so we add 2. Oops, 5. Max left is 2, so we add 1 here. So 6 is the answer. Okay. So we can step through now. So basically, we have pointers, and they'll either be we have pointers, and we're going to slowly close this window, and we process the smaller of the two pointers, because knowing that it's smaller, we know there's a wall on the other side that's greater that will be there to block the water if that's the case. We also keep track of the max on the left to be able to trap the water, essentially, because anything lower than the max is water that we have trapped. But it has to be a rolling max, and we continue to iterate and trap the water. Okay. I don't really know if that's a great explanation of me doing it, but oops, we're gonna write trapping rainwater here. Cool. Stack, jeez. Okay, so this, we're gonna use a stack. We're gonna use a stack to store all the opening parentheses, and whatever's on the top of the stack, if we encounter a closing parenthesis, it has to match whatever's on the top of the stack, or else the algorithm, or it's not a valid parenthesis because it violates the the LIFO structure of the stack. So we'll add all the opening parentheses to the stack. Whenever we encounter a closing parenthesis, it has to match with the top of the stack. If it doesn't, then we're cooked. I should probably do dot equals because it's the wrapper class. See, okay. This might be wrong right here. And I don't know exactly where it's wrong, but let's find out. Oh, whoops. That's why. So the reason why we don't do it is because you have a mismatch. We can have a valid opening and closing, but a mismatch in the type. And what? Oh. Yeah, we can have a mismatch in the type, and if we return false immediately, it'll break. But this broke, so let's see what's happening. Oops, it's this. There we go. Cool. Space complexity is... Oh, I didn't go space complexity for the other one. Space complexity is O of n. Time complexity is O of n. I'm going to write this down too. Trapping rainwater, it was time complexity of O of n and space complexity of O of n as well. Min stack, jeez. O of 1 time complexity for each function. Okay. So for this, we're going to have two instance fields. We're going to have a traditional stack, and then we're going to have a min stack. And what these are going to store are, this stack is going to store a traditional stack if you were to have all these operations on it, and the min stack is going to store the minimum values as they come in. So it will store -2, and then if we push 0, it'll check what the most recent minimum value is, compare it, and see if it's smaller. If it's not smaller, then we're not going to add it. If it is smaller, then we're going to add it. So -3 would be added. So in this simulation, stack would equal -2, 0, and then -3, but then min stack will equal -2 and -3. And then if we pop -3, we're going to take that and check if that is the value in the min stack. And if it is, then we're going to pop it. If it isn't, we won't pop it. So for example, if we pop 0, we're going to check if 0 is the top of the min stack. It's not, so we're not going to do anything. And then the same with -2. And we'll see it's -2, so then we'll erase it. So that's how pop will work. That's how push will work. Top, we just peek to the top of the regular stack, and then get min is we peek to the top of the min stack. So yeah. This side of stack. Okay, so and the reason why I do the equals here is because these these stacks use the wrapper class, the integer wrapper class, and you have to use the equals operator rather than the comparison operator like this, because they will actually not equal. If you have two numbers that are in the stack, they will not equal because the reference value in memory is technically different, although the reference in the heap, actually I'm not going to explain that, but the reference value is going to be different despite the number being the same, essentially. So you have to use the equals operator to do a deep comparison of it, because these are now objects rather than primitive values. And then here I can just do return this stack dot peak, and then same here, return this dot min stack. Empty stack exception. Oh. Min stack is empty. There we go. This is O of 1. 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 So, yeah, and then the min stack is O of n space overall. Oh, wait. Okay, so we're going to use a stack here that stores integers. And we are going to, whenever we encounter a number, we are going to add it to the stack. And whenever we encounter an operation, we are going to apply that operation to the top two values on the stack. Because we want to have 13 divided by 5 here. And then after that, we're going to push that output value back onto the stack. And then we'll have 4 plus 6. Or 4 plus the answer to this. Right there. So the stack will allow us to keep the order of operations because it's in reverse Polish notation. So yeah. So I'm creating a stack. I'm iterating through all the tokens. I'm going to create a switch statement for each token. And if it fulfills these cases, plus minus multiply divide, so if it fulfills these cases, then we're going to do those operations, and then we're going to default by taking the stack and pushing the integer value. Because we know if it's not any of these, it has to be a number. So here we can say stack.push stack.pop plus stack.pop. So this just adds the top two most values in the stack, and then here we need to store the terms. So term 2 I think equals stack.pop, and term 1 stack.pop, and then we need to say stack.push term 1 minus term 2, I think. No, it's the opposite. So something like this. Yeah. Wait, is it? No, yeah, it is like this. Yeah. And we can do this because addition has the commutative property and subtraction does not. And we can do the same for multiplication because multiplication has the commutative property, but we cannot do it for division. Denominator. And return stack.peak, the top of the stack. Beautiful. So this occurs in O of n space complexity and O of n time complexity. Okay, we need to generate all combinations of well-formed parentheses. So what we can do here is, because we're creating all perfect, not all permutations, but all perfect permutations where it satisfies this condition, we can use a backtracking algorithm to be able to create those permutations. Generally, when you have permutations and combinations and you're trying to create them, using backtracking will create all the permutations, and then you can filter in your backtracking method for certain conditions that you want to satisfy to be able to filter out a few of the permutations that don't necessarily fit the criteria that you want. So we'll create a backtracking method and we will create permutations and then set the conditions for it to satisfy this well-formed parentheses. So what we can do is we'll create our output array, our output list, and then we'll backtrack. We'll start with 0, 0, n, and then output, and we'll return output. So we need to keep track of the opening and closing parenthesis amounts, and that's what these two values are. And then we have the n and something like, oops. Yeah, something like this. So if n, or if open plus close equals n times 2, we're going to take the output and add, actually, we also need a string builder object because we want to be able to create the permutations. So, okay. I don't know if this is how you do it, but yeah. Okay. So if our open is less than the n amount, then we're going to take the string builder and append an open parenthesis to it, and then we're going to backtrack. Increment open, add all these values, and then remove it. And then if the close is less than the open, we're also going to backtrack. And I believe that should work. Yep. Beautiful. So I guess I can explain this a little more. We never want to close any parentheses that aren't already open. If we have more closes than open, it'll unsatisfy this well-formed condition. So the reason why we have this open is because we want we want n openings, but we don't want more closes than opens because that dissatisfies the condition. So as long as we have these two, we are good to go. Yeah. Backtrack. Oh, this is complicated. The time complexity and space complexity of this goes complicated. So, time complexity, space complexity for this is O of n times 2, so O of n. Oh, actually, no, it isn't. It's O of n times it's the amount of permutations. So, here we have. The call stack will never be greater than n times 2. So the call stack will take n memory. Yeah, like 2n memory. And the time will take... What will the time take? So I think memory is O of n because the call stack is taking up the most memory. Time. O of... I think backtracking is typically the number of subproblems as the base and then n as the exponent. So it's 2n. Or it's the other way around, n2. I think it's 2n though. Let's do some... tree recursion calls. There are 2n positions each. Jeez, bro. That did not make any sense. What was my speed on this? 100%. Why is it the speed that it is? Yep. There we go. Yep. How do they know depth is n? So what's our branching factor here? Two n. Maximum depth is 2n. Yep. Why is it 4? Makes no sense. Okay, we'll just add this. I just can't explain. Recurrence relations are pretty hard. Okay, daily temperatures. Okay, so we can use a stack here. And basically we store each value, and then when we store the value we're trying to compare in the stack, and for every value that's greater than it, or sorry, for every value that's greater than it, or not greater than it, we add to the stack until we find a value greater than it. So we create a monotonic stack, And then when we encounter a number when we encounter a number like this where we're checking 71, so this is going to be 1 because the next is 74. This is going to be 1 because the next is 75. And then this is going to be more. So 71 is not bigger, 69 is not bigger, 72 is not bigger than 75, and 76 is not bigger. So what we'll do is we'll add 75 to the stack, add 71, add 69, and then add 72. Add 69, and then we'll encounter 72. And what will happen is we'll process 69 as the top of the stack, and we'll recognize this is bigger. So we'll make this 1, and then it'll check if 71 is less than 72, which it is. So we'll calculate this as 2. Then it'll calculate, we still have this in the stack, and we'll calculate 75 and compare it to 72. I'm probably explaining, this is a really bad explanation. How do I rephrase this? Basically, we store variables in the stack, and we compare them to the current. We'll loop through all these and compare values in the stack that have not been solved by the current number. And if we find that the top of the stack and the current number is greater than the top of the stack, then we can calculate the distance between those two values and then input them into an output array. Does that make sense when I explain it? We use a stack to store values. We use a stack to store indexes for values that are not yet solved. And when we encounter values, as we loop through this array, if we encounter a value that is greater than the top of the stack, we will pop that off the stack and calculate the distance between those two values. And if we continuously do that throughout the rest of the array, we'll get our answer. So here I can do output. So while the stack, I'm not explaining myself. So we're going to store the length of the array here. We're going to make our output array and then loop through all the values in the temperatures array. For each value, we're going to check if the stack is empty, if the stack is not empty, so if there's a value, and if the value at the top of the stack is less than the current value. And we're going to throw this in a while loop because we want to run this as many times as possible, because this will allow us to find the shortest distance. So if we do find something, then we're going to say, okay, the output value for that value is equal to I minus stack.pop, and then stack.push I. And this should be it. Oh, whoops. There we go. Space complexity is of n, time complexity is of n. Cool. Car fleet. Oh, okay. Car fleet. I've tried to learn this and tried to explain this. Actually, I can explain it. So what we'll do is we're going to take all these positions and all these speeds. Actually, sorry, we're going to take all these positions and calculate the distance from the target. And then we're going to divide all those distances by the speed to be able to determine the time it will take to get to the target. And we're going to store them as doubles, not just integers, to be able to calculate the exact speed. And then once we do that, what we'll do is we'll sort this position array and iterate it from greatest to least, so backwards, from right to left. And when we do that, we're going to we're going from the closest to the target to the furthest to the target, and we'll iterate. Actually, I need to backtrack. So, okay. Oh, this is complicated. So, let's see. It's probably better if I type it out, these complicated ones. So, we'll calculate position, or calculate distance, each position's distance from the target, and then calculate the time it takes for that position to reach the target, and store those values in a hash map with position as the key and speed or time as the value. Okay, and then after that, we're going to sort the position array, and then we're going to process from closest to furthest. So every time, and then every time as we iterate, we store the we store the previous speed. We store the previous speed as we iterate. If the current speed is greater than the previous speed, that car has caught up and we have a fleet made. And then we keep on doing this. And then we keep on doing this. And then we count all the fleets. Yeah, so that's what I'm going to do. And then we can return the fleets. So let's do that. So we're going to calculate each position. So first, let's make a hash map. We're going to use integer and then double. We're going to put the position and the target minus position divided by speed I. There we go. So now we have calculated each position's distance from the target right here, and we calculate the time it takes for that position to reach the target by dividing by the speed. So we take the remainder distance and divide by speed, and then convert to, or cast it to a double, and that will give us our values. So then we need to sort the position array, and we need to iterate through it backwards. So okay. So we're going from closest to furthest. And then we're going to store or double prove speed. And then yeah, something like that. So then here, it probably would have been better if I did like something like this. Add comments here, boom, added this here. Yeah, something like this. So we have initializations here, and then we have a calculation here. Yeah, something like that. This is here. It's a computer science homework, kind of. Process closest to furthest. Yeah. So here we have this. And we return fleets. And then here, map.get position I, or if map.get position I is greater than prev speed, fleets plus plus. And then prev speed equals map.get position I. Let's just make life easier for us here. I don't like using the greater than for some reason. Yeah, I think that's it. There we go. So I actually did a pretty good job explaining it once I typed it all out. Space complexity is going to be O of n here. Time is going to be O of n log n here, O of n here. So time complexity is O of n log n because of the sorting, and time complexity is time complexity is O of n log n because of the sorting, and then space complexity is going to be O of n because we store all the positions. Yeah. Nice. Nice. Not too bad, not too bad. How many do we solve? We solved 10. Okay, nice.